Before others could join, let me do a quick recap on what we have discussed in yesterday's session. So the way we have initiated discussion yesterday is basically, to talk about the Spark streaming module. So where we try to understand the differences between the batch programming versus streaming applications. And we realized the importance of streaming applications across various domains, including like travel, healthcare, or even different other sorts of domain. It's not limited to a specific domain, but it's kind of now becoming an industry standard for big data applications to support streaming data requirements as well, not just the batch processing kind of environment. Basically addresses to handle the streaming data. So one thing we are all sure that even though we call Spark streaming module as in a real-time kind of system, but it is in reality, it's not a real-time solution. So we understood the key difference between a real-time system versus the micro batch environment by comparing between Apache Storm versus Spark streaming. So where we have understood that in Spark streaming module, you have to set or define a specific interval, and whatever the records coming into the system will be grouped together in that particular interval, and that interval could be as small as 1 second or even half a second or 1 minute, 10 minutes or 15 minutes. Depends upon the volume of the data you capture in that particular interval and depends upon the source systems itself. So each domain has different data sources. Each domain has different set of requirements and the data inflows and all that stuff. So that's why depending on that you choose a matching interval to process the data. However, once you collect the data in that small interval, so-called small interval, you actually do the batch analysis on top of the data. So that's where we have seen how Spark actually has come up with a new data structure called as DStream. DStream stands for discretized stream of objects. So when I say discretized stream, it is basically nothing but a combination of a group of RDDs coming into the system, without any timeline. So it basically you keep generating the RDDs within your DStream depending on the interval you configured for your streaming application. So we also seen a very interesting example in the sense that we tried to create a client-server kind of application using simple netcat kind of environment where we tried to produce the records from the netcat and then we tried to consume that from our Spark streaming application by creating the Spark streaming context. So as you all know, so far we have been working only with the Spark context instance, which was like an entry point for your Spark applications, right? So now that we understood there is another context instance available for us designed for streaming application is called as Spark streaming context instance. So you use that to define the interval and to spin off your application, and the application will run forever and it will just keep listening to the input data services, and basically it works in a pull model, right? So where your Spark streaming application is responsible to pull the data. As in, it could be a Kafka message queue, it could be a Flume, it could be a HDFS, HBase, whatnot. See, whatever the input data source where the data is available, everything could be considered as an input data source. All that it matters is you just have to implement the connectors to the underlying data source to be able to capture the data. Okay, so by the way, we also understood you process the data in Spark streaming module just like any other Spark application. Just run the MapReduce on your DStream. Maybe slightly the methods could be different, but overall the concept is same. Okay, there is no major learning curve involved. If you are familiar with Spark context, as you have noticed by now, since there is no major deviation other than understanding some specific functions designed for streaming applications. Okay, so it's just like learning some other API. And then finally you store the data into any destination, which could be possibly like HDFS, NoSQL databases like HBase or Cassandra, whatever the storage you would consider feasible for your application. You just go ahead with that and process the data into that particular storage system. So now let's try to understand some of the advanced topics within streaming applications, folks. Okay, so for any questions you guys have which I have to handle, or maybe if you guys have any concerns, so feel free to rise before we go ahead and initiate with our discussion for today. Anyone has any questions, so feel free to ask me now. Ajay, Anand, Ashok, Bishwajit, Jagadish, Sandeep, Ram, Rehan, Reggie, Satish, Satya, Shakti, Shravan, Shushma, and Venkat. So pretty much a long list of participants in this session. Okay. Excellent. So looks like pretty much everyone is good so far. There are no concerns as of now. So let's proceed further. So folks, I hope you came with a lot of energy for today, because we are deep diving into some of the most exciting features today. Okay, we cover some of the most exciting features available in Spark framework. Specifically, we cover the entire, now the advanced topics within streaming. Then we'll move on to a machine learning library, where we try to understand the overview of machine learning algorithms and how a data science project will be implemented in a nutshell. And then we move on to implement one project for today, which is we try to build a movie recommendations platform. Then we also cover the Spark SQL module in detail. So in VAST, we'll try to complete the SQL module, folks. Okay, so let's try to get on to the discussion, get on to the ground now, and try to. Okay, so here is the first slide. So basically it talks about window operations. This is an additional feature available in streaming module. Okay, so now that we all understood, right, that you configure an interval, say for instance you configure an interval as 1 second, or maybe 15 seconds, or maybe 1 minute. Whatever the interval you configure, what happens? Basically whatever the input records been pulled from your module, from the Spark streaming application, will be batched together as an RDD. Okay, let's say let's say you see 1000 records in 15 minutes. Okay, all those 1000 records will be kept in an RDD. Let's call it as RDD1 at that particular interval. And then the next batch, next 15 minutes, whatever the records enters into the system, let's say another 2000 records, so that will be grouped together as another RDD. Okay, so here Spark allows you to perform some windowed operations as well. Even though you collect at some interval like 15 minutes, 1 second, or 1 minute, however, let's say if you want to perform certain operations across these groups, let's say if I have certain requirement, like for example, I wanted to perform some operation at 1 hour group. Every 1 hour, whatever the batches appearing into the system, I want to process that 1 hour data as if it's a single source. I just don't want to divide them into 15 minutes. Instead, I wanted to cover every batch. Like if you consider 15 minutes batch, then you get 4 batches, right? So I want to process that 4 batches in one shot. So what is the best way to do that? Is there any such flexibility? However, one basic option is you guys can recommend me saying that you just set the interval to 1 hour, then our job is done. Yes, of course we can do that. There is no harm in doing that, in processing the data. However, the another way, the recommended approach is basically to use windowed operations. In windowed operations, as I shown you yesterday, let's say if you are getting the streams of data at every interval, let's say first 15 minutes you get one stream of data, which is on RDD, RDD2, and then RDD3. So you actually group them together and then apply your functions. So now whatever the functions you apply, so it will be applied on all these three RDDs. Okay, because you are windowing the operations. Let's say if I window the operation as 1 hour, for instance. Okay, so then you have got 4 batches, right? If it is 15 seconds interval. So then you actually run some functionality, some business logic across all these 4 batches of data. Okay, so this is something called as windowed functions or windowed operations. You can see pictorially here. You get the original data stream here, this stream here. At time interval 1, you got one batch, 2, you got another batch, 3, you got another batch. You group together them by specifying some top level interval, and then all the data will be merged together for performing certain specific operations. Okay, so you no need to worry about grouping these RDDs together. Instead, you leave to the framework how it handles your aggregation functions on top of these batches. So there are some functions. There is no major learning curve as such. So even though conceptually it sounds like a big topic, but if you look at the learning curve, it's fairly small. Okay, see here, it's just about understanding some functions in that D stream. So one is like window length, slide interval. You just specify both window length and slide interval. So return a new D stream which is computed based on the window batches of the source data stream. So you have to specify the length of the window and then the interval as well. Then count by window. So you can also say count by window. Return a sliding count of elements in the stream. So it just returns the count across different batches. Then you've got another function, reduce by window. So pretty much the basic functionality what we discussed, right, on top of RDDs, it remains still the same. But the only difference is it will be operated on multiple RDDs rather than just one RDD. It will be operated on multiple RDDs in that particular window. Okay, so but the functionality remains the same, folks. There is nothing different. So you're passing the function, window length, and then the slide interval as well. Let's say reduce by key and window. So when called on the D stream of key value pairs. Okay, so it basically does the aggregation operation on the based upon the key. It does the aggregation functionality on top of the values. So Ashok says, what is the benefit of window over the original stream? I see only process getting delayed. See, the way you could treat this, Ashok, basically, let's say you have couple of functionalities. For instance, let's take about a business intelligence screen. Let's say there is a dashboard, for instance, Ashok. So I have a dashboard which will be monitored by some business analyst. And that business analyst might want to monitor what is happening every 15 seconds, for instance. And might also want to do the aggregations of the 15 seconds to up to like, let's say 1 hour and see what happened in the last 1 hour. So it's all about business analytics, right? So you are performing some operations at a short interval, and also you are accumulating and doing the operations at a little bit bigger, slightly bigger intervals. So both you can apply. So you can normally run your functions using the normal D-stream functions, and you also do this for doing some aggregation across the across multiple intervals. Ashok, does that make sense? Does a business analyst would like to see the different aggregated values at different time intervals? My answer would be yes. Okay. Then Rehan says, so if I have 3 time intervals, let's say time 1, 9 AM, 1 million records, RDD 1 time 2, say 1.2 million, whatever, blah, blah, blah. And then in the above use case, if we use windowed operation, the window will merge the records to 3.7 million records. before applying any transformation on it. Yes, absolutely. So that's what it is, right? So it basically applies on all the RDDs. So how it internally happens, we just leave it to the framework. Typically, it will merge internally and then we'll apply your operations on that bigger RDD frame. Okay, Rihan? So is that clear, both Ashok and Rihan? Sure. So let's move on. So count by value and window. So this is basically the same story. So it just counts the values at that window. So guys, let's have a quick look at how we implement the functionality in windowed operations. So I'll take the same example, by the way, but I will apply the windowed operations on that example. Okay, I'll call it as windowed network word counts. Okay. See here, I've got the windowed network word count, and I'm instantiating the Spark configuration instance, then instantiating the streaming context instance using it. By passing the interval as 15 seconds. Then I'm saying a socket text stream. So this is where it will again listen to. Then flat map off. So basically it is just splitting each line and aggregating all the words together using the flat map. And then the code below. Okay, so now I'm performing it windowed operations. Like let's say words.map off. So I'm taking this analysis like x comma 1. So instead of performing at every seconds, then what I'm trying to do here, reduce by key and window at 30-second interval. So instead of 15-second interval, I'm just saying 30-second interval. So there is the function which has to be applied to all the records, and then this is the interval, the window interval. And then word constant printf, which is pretty much similar. Okay. So is the code clear? So additional thing we just performed, the only additional step we did is this one, reduce by key and window. You can perform normal word count at this interval, and you can also do this as well. Okay. So now that I already have this jar file been created yesterday, right? So it has already packaged that job as well. So I'm going to use that job directly, folks. Okay, so let me start quickly my Hadoop. So once I start the Hadoop framework, then I'll go back and run the windowed operations example. So let me see what is the path being referred in this job. Okay, so this is not the path, right? It is directly looking into the socket. It's kind of a socket programming where we are actually listening to a particular port for the data to be available. Any further questions, guys, so far? Are we good? Let me first start the netcat when the program nc netcat, right? So let me just check the command for that. nc-lk, okay. This is the port where I'm trying to push the data, and let me run the job quickly. Spark submit class is what's the class name here? It's basically this windowed network word count is the class name. And then the jar file name is hello Spark. Okay, let me run this program. So now this program will start. However, instead of calculating the word count at 15 seconds interval, which is as per the actual configuration, but it does the word count process at 30-second interval because of the windowed operations. So basically it accumulates two batches, which is at every 15 seconds there is two oddities, and then will do the aggregation operation. So if I just generate some data, so you'll notice the data here. Okay, and this is running every 30 seconds. So you can actually check the timestamp because this is in long format. You may have to convert this into the actual timestamp so that you understand the difference. Okay, are we all good so far? Shakti says, is there any advantage of window functions over directly providing durations directly in the program? Okay, performance wise or something. So Shakti, as I told you just before, when Ashok asked probably the similar question. So as I answered, so there will be some kind of a business intelligence dashboards where you might have to do aggregations at the smaller interval versus some of the bigger intervals to understand the system at different intervals. So that's at an use case point of view. So in terms of performance at technical point of view, other than there is only one benefit. So instead of loading too much of data into one single RDD, so here we are having multiple RDDs, so which could be a much more easier way to actually handle the data. So probably this could be useful, especially if the volume of the data is quite high even at shorter intervals. So you can't actually afford to pull such huge amount of data on a bigger interval. So at that time you can go with this. You specify a very small interval to pull the data first and keep it as an RDD within this part, and then you apply the actual transformation at some higher window. So that could be another technical point of view, that could be another benefit. So instead of handling the large volumes in a single window, pulling such data could be time consuming versus creating shorter RDDs and then applying the process within the RDD at some longer intervals. Okay, does that make sense, all of you? Any further questions? Sure. So let me stop the application now. So let's proceed to some other functionality within the Spark streaming applications, guys. So this is very, very interesting and important too within the Spark streaming applications. Let me first ask you a question before we actually go ahead and understand this functionality called as checkpointing. Could you all tell me what happens if a Spark streaming application which is written as part of the driver program, right? So all the programs we are writing are basically driver programs. So let's say my application has started, my driver program has started and it is running forever. It is supposed to run forever. Due to some reason, maybe because of some hardware failure, or maybe because of some power shutdown, or due to some of the improper handling of exceptions. It could be any reason. Okay, let's assume your program has went down. Now your program has it has been processing in a day. It has started, it has processed so many batches, and it has went down at, let's say, around 1 p.m. in the afternoon. Okay, now the administrator realized that, okay, so the driver program, I mean the streaming application, has went down. Now if he restarts that particular application, what would happen? Could you all tell me? So the application went down at 1 p.m., but however you noticed it at 2 p.m. and then started by 2:15 p.m. You did some necessary workaround, and then you started the application again at 2:15 p.m. So could you all tell me, is it possible to recover from the exact state where the program has been failed? So by the concepts we have learned so far, is it really possible to recover from the exact state where we have actually failed? This question is for everyone, folks, by the way. Okay, say yes or no. It's just a simple thing, right? Okay. So Shakti and Ajay has some answers. Say that why don't we leverage on lineage? Okay, so that's a good point, but it does not work. Let me explain. Lineage is available at what level? Lineage is available with RDD, but here we are dealing with D streams, discretized streams. So we don't have that information that, okay, how many RDDs have been processed, from where you have to start again. Okay, we don't have that information. So lineage may not be helpful in this case to be able to recover the system from the exact point of failure. However, Spark streaming comes with a new functionality called as checkpointing process. If you enable checkpointing on the Spark streaming application, what the application does basically is, whenever it processes a particular RDD within the D stream, immediately it will log that information onto the disk as some kind of metadata into the disk that it has processed this particular interval, this particular RDD with X number of records, and the process was successful. So in that manner, it will try to keep or persist the data into the disk. Even if you assume that there is some lineage available as part of the D stream, however, considering about there is a memory failure, and since you could not recreate that D stream, you cannot retrieve back that information because that lineage might be available in the memory, and you will lose that once there is a memory restart or memory failure. However, using the checkpointing process, since we are keeping the data, persisting the data onto the disk every time you run the operation at every interval, at least you have a track of what has been processed and what has not been processed. In this scenario, the next time when the administrator go back and restart the application at 2:15 p.m., then with the checkpointed directory, okay, where actually the state has been stored. Now Spark streaming application is so intelligent that it will read the state from the checkpointed metadata, and then will try to restart the process from that exact point of failure. So it will start processing the records from 1 p.m. till 2:15 p.m. and further intervals will get processed in general as usual. Okay. So this basically is some kind of fault tolerance mechanism being incorporated within the Spark streaming applications to be able to handle such kind of errors randomly. Okay. So Ajay says similar to restore point in Windows for restoring later on. Right. Okay. Will the performance do not deteriorate? Okay, so yes, it comes with some kind of overhead, right? However, the overhead is slightly, it's negligible. Okay, even though it has some additional overhead, I would not deny that statement, but it is negligible kind of overhead because see, when you consider you are processing 1 million records in an interval, so the processing time would be quite high for processing each record in 1 million. I mean, if the processing time would be quite high for 1 million records processing. However, to just persist the metadata into a disk with some information, right? It's kind of a log you are persisting into the disk in some format. It's just one single IO operation. Okay, I don't see that it's kind of a bottleneck. At the same time, it will have some kind of overhead, considering the intervals are quite shorter. If let's say if you are having interval of 1 second, then every 1 second you are making the disk IO, so which will considerably increase the it will considerably impact the overall performance of the system. However, if you are processing the records like at a minute level or even at 15 minutes kind of time frame, I don't think it has to be, we have to really consider about it. Okay, then it becomes like very negligible in terms of the amount of data you're trying to process. So are you all clear now? Ajay, so Ram says the entire D stream RDD is getting stored in the disk. Not really, Ram. Okay, so it will not store the actual RDD itself. Rather, it will store the metadata only in the form of the log. So the next time what it does is it will go back to the source system and will pull the data again from the source system from that point in time. Okay, let's say if it is a message queue will have the data. So it will go back and retrieve the data from the message queue from that point in time. So then Satya says, but what if the data capturing process is dynamic? Won't there be any data loss? So as I just said, the source systems also are capable of handling this fault tolerance, right? Like if it is a message queue, it by default maintains the data. Even though you process a record, it will still have that record for some period of time. Okay, so you have to carefully design the entire system configurations to how you maintain the source system datasets as well to handle the fault tolerance mechanism. Ram and Satya. Shakti says, so is there any property which needs to be enabled to do so we provide the checkpointing? Yes, I will come to that, Shakti, don't worry about it, I will come to that. So basically, typically how it looks like for doing the checkpointing, so it just needs to set up a Spark streaming for fault tolerance. It allows Spark streaming to save data periodically. So the data could be stored either on the checkpointing data, right? You can store it on HDFS local file system or even S3. So any of the storage systems you can store the data. If the driver fails, it can be restarted using the saved checkpoints. This is called metadata checkpointing, and here metadata include configurations, dstream operations, incomplete batches. So all this information will be stored in the checkpointed path. So while writing, this is how it looks like. Your driver will keep writing that information into the disk. So when you restart the application after failed, so it will read the metadata from that disk and will retrieve the state, and then will start processing the records from there onwards. Okay, the only step, the only thing you are supposed to do to enable the checkpointing is to just make a call on the Spark streaming context. The method name is checkpoint, by passing the path where it should supposed to store the checkpoint metadata of the checkpointing metadata. Okay, are we all clear so far? Shakti, Satya, Ajay, and Ram. So Sandeep has a question. If ARN is used, fault tolerance, okay, can be handled by ARN architecture. Do we still need this checkpointing? We still need this checkpointing, Sandeep. Okay, So this is still required. Okay, so ARN is a separate story. So basically, when you run the application, ARN is capable of running each and every task. It will have the metadata at the task level. But here, okay, it will not have the information about what is the source system, till what time we have actually processed the data. That granular information will not be available with ARN. Even though ARN could do the fault tolerance handling at the task level, if the task is failed, here we are talking at the system level where the entire Spark application goes down for some reason. Okay, so if say if your driver program goes down for some reason, there is no way for you to be able to retrieve till what point we have processed that records. Okay, because that information is available only with the Spark streaming application driver. So that's why we have to do this process additionally, and we can't rely on top of ARN for doing that. Does it make sense, Sandeep? Okay, so let's move on here. So guys, all that there is a program, so let's get on to the program. It's the same thing here, listed here. So first let me explain the program and then we can come back to this. So let's directly, let me walk you through the program. So it's a very big program, by the way. So your concentration or your concentration is highly recommended, okay, for this program, folks. Okay, so not this one, right? Recoverable network word count. So this slightly bigger side of the bigger program. So let's concentrate, folks. So let's. One is file, character set, files, and then accumulator, spark conf, spark context. So there is some concept called as accumulator. This we might probably cover today depending on the availability of time in the end. Okay, just imagine accumulator as if it's a counter for time being. Don't worry about it too much since we are having dedicated program for accumulator. This basically is a kind of counter in Hadoop. Okay, here in Spark we use accumulator for doing the counting of the records being processed. Then broadcast, then RDD, and then broadcast is also another type of variable in Spark. We'll discuss this in detail later. Then RDD, we all know about it. Second, streaming context, and then time. So these are all the classes we are including from Spark streaming module. So let's have a detailed overview on the program itself, folks. So I have written an object called as say this is word blacklist, forget about it. Dropped words counter, forget about it as well. So let's start with this recoverable network word count program. So what I'm trying to do here, I have written a method here, a function. So this function, let's see what it is trying to do. Create context. So I'm creating some context. I'm passing the IP, port, output path, checkpointing directory, which means I am expecting some input parameters from the user. So user have to supply some input parameters, and those parameters have to be passed to this method called as create context. So before starting with this method, right, let's start with the main method in the program. So in the main method, okay, we are actually supplying some arguments here, which are command line arguments. When you run this program, you have to supply some command line arguments to this program. Okay, and that should not be less than 4 parameters. So you have to at least specify 4 parameters to it. Then you are supposed to pass these following parameters. One is your arguments are, okay, so it just prints those arguments here. System.error.println. In case if this does not meet this 4 parameters condition, so it will automatically exit. So user has to at least supply 4 parameters to this program to be able to run the program. Okay, here is some help kind of content. The recoverable word count, host name, port, checkpoint directory, out apply. And then hostname and port describe the TCP server that Spark Streaming would connect to receive the data. This is the same netcat program which where the server connects to, the client connects to this particular server. Then checkpoint directory, the directory to HDFS compatible file system with which checkpoint data and file to which word counts will be appended. So basically this is where the directory used for storing the checkpointed metadata, and this is the file where the actual metadata will get stored. Then in the local mode, master should be local of n. So you can also run this application in the local mode as well. Both checkpoint directory and output file must be absolute paths. So ensure that you pass the absolute path for this both these parameters, not the relative paths where you're running the application. Okay, so now that we understood what parameters are required to run this application, now let's see what I'm trying to do with those parameters. So I'm just creating an array with all the arguments. I'm calling this an IP, port, checkpoint directory, and output path, which is file. And then Spark streaming context get or create. I'm invoking a method called as get or create. I'm passing the parameters like checkpoint directory, and then in this I'm actually invoking a method called as create context method, with which I'm passing all the parameters like IP, port, and all the stuff. So now taking this method, so let's see what this method basically does. So I go back to this method create context. So this method takes all these parameters and returns a streaming context instance. That's what you can see here. It takes a Spark streaming context instance here, and it will be started here. So by the way, what this is trying to do is println of creating new context. So it's just this is kind of a debug statement, just ignore this. And then output file is equal to new file of output path. So I'm instantiating the output file. So if that file exists, I'm just deleting that file. Okay, then Spark configuration instance, new Spark conf of set application name. So recoverable network word count, set master of this path. Then value SSC is equal to new streaming context. I'm passing the Spark configuration instance and then the interval to it, so that I create the Spark streaming context instance. So far it is very clear, right? I'm just instantiating Spark configuration, then instantiating streaming context. Then immediately I am invoking this method called as checkpoint method, passing the checkpoint directory to it, where it can maintain the metadata of the data being processed till that point in time. Okay, so this is the only additional step. Apart from this, let's see what I'm trying to do. So then Spark streaming context at socket text stream IP port. This is the same thing. I'm connecting to that particular port and listening the lines. So once I get the lines as if it's an RDD, then lines.flatmap of _split of space. So it basically splits each line with a space character and returns all the words accumulated together to this words RDD. So once I get this words RDD, I'm invoking the map method to it, and I'm just emitting word followed by its count as 1 and then reduced by key as _+_, which basically is doing that in a summation operation, and then doing the actual word count process here. So once I get the word counts, which is key value pair, the key being the word and the value being the actual count of that word in that particular interval, word counts that for each RDD. So for each RDD in the word counts, I am trying to do some operations. Okay, what is it? Let's have a quick look into that. So one is I'm taking that RDD here. So I'm retrieving each RDD here from this RDD. I'm taking each RDD for this time interval, and then what's blacklist of get instance of Spark context. So get or register the blacklist broadcast. So let me go to this word blacklist method. So this is an object, right? Word blacklist is an object. So here, what I'm trying to do is basically I'm having a method called as get instance method, in which I'm defining a sequence of words like A, B, C, and I'm making it as a broadcast variable. Okay, I'm making this list A, B, C as a broadcast variable. Let me take an opportunity to explain what is a broadcast variable. So guys, please concentrate. Okay, so folks, broadcast variable in Spark basically indicates that it is a distributed cache. It is not a cache, rather it is a distributed cache. The difference is, in cache you just persist the object, it will get distributed. The RDD is already set. But distributed cache means, let's say if you are dealing with two files, one file being some terabytes of data, which is massive, and another file being just 200 MB. Okay, if you are trying to do the join between these two files, one with 4 terabytes and one with 2 MB, essentially the performance could be pathetic, especially because these two files are not of similar size, and one is small and one is quite big. And if you apply the normal distributed concepts, and if you try to join the two data sets, it would take quite a long time. The workaround for this is you can put the small file in all the nodes, because it is just 200 MB and it can fit into memory easily. You can actually put this file into all the nodes where the tasks are running to process this job, and it can actually look up into its own node to read the data from that node while doing the join operation. This way the join will be more efficient. So in this, what you are trying to do essentially is you are copying a file across all the nodes within your cluster where this particular job is running. Let's say consider your job is running in 100 nodes in your cluster. This particular file will be copied to all the 100 nodes. This is something called as distributed cache in Hadoop. Similarly, we also have the same concept here, analogous concept here in Spark, called as broadcast variable. Whenever you define a broadcast variable, if it has some set of data, that data will be copied redundantly across all the nodes within the cluster where the particular job is running, tasks are running for that job. The only purpose is, since this feed is quite small, copying it into all the nodes it will improve the performance drastically, because it does not have to go to the network to read the data. Rather, it can directly read the data. It can directly look up the records from that small file from within its own node. Okay, that's the concept between the broadcast variable, folks. Here, by now you understood what's the purpose. It's basically blacklist words, which means if you get the stream of lines, I'm not interested in some words which are not required for me, or which does not see the for. Okay, so these kind of words are even actually sometimes referred as stop words, are blacklist words, which are not really make sense at all. Let's say if you're trying to find out the patterns of the topics, let's say for Twitter application, then Do you really consider the for these kind of words? No, right? You just consider words like, for instance, sports, or for instance, say politics. So these kind of words you consider to determine the uh, trends. So similarly here, I'm not interested in these kind of words. I'm creating a broadcast variable by passing this list of arguments to it. So now that I have this broadcast variable, I'm just invoking this method spark context dot broadcast of word block list. So this will copy this sequence, this array, to all the nodes in the cluster where this particular job is running. So if I come back again here, so this is basically like so now that you got that file, that block list words in all the nodes, so I'm proceeding further here and I'm getting the instance of dropped words in counter. Okay, so let me wait here. Okay, let me complete this and I'll come back to these questions. Okay, so dropped word counter. So dropped words counter, what is it? Dropped word counter. So it's here. So in the drops words counter, so I'm just checking, I'm getting the Spark context instance and sc.accumulator of words in block list counter. So at the same time, okay, so I have actually specified some kind of broadcast variables which will be put into the distributed cache. So the idea is to basically ignore these kind of words if they appear. Here, at least I also at least want to track how many such words have been dropped from the actual stream. Then I have to do counting of such words. Since we are doing distributed data processing, there are every tasks running in isolation with each other. Let's say task 1 running in node 1 can drop 10 words. Task 2 running in node 10 might drop 100 words. So here each task is actually dropping certain X number of words. In order to get the count of how many words have been dropped throughout the program, you need to use some kind of counters. In Hadoop, there was a concept called as counters. You can define the default counters or user-specific counters in Hadoop MapReduce. Here, there is nothing like counters, but there is another similar concept called as accumulator. Accumulator is very much analogous to the counting of a specific counting. It's analogous to counter. So since that I'm dropping certain words from the input stream, I also wanted to keep track of how many words have been dropped. So I'm using an accumulator called as words in blacklist counter, and initial value for this counter is 0. Okay, that's what I'm trying to set here. And then this and then after this I'm getting the dropped words counter, then rdd.filter off. So case word count, then blacklist.value.count contains word. So if it contains this word, blacklist value word, then dropped words counter will be increased, and then this will be ignored. So this particular word will be ignored because this is in the block listed word. So all that I'm trying to do in this 4 lines of code is basically I'm retrieving the block listed words. I'm checking whether this particular word is matching with any of the block listed words or not. If matches, I'm filtering that word. Also, I am doing the counter by invoking this counter here. Okay, else true. If that is not falling in the block listed words, I am just returning it as true. So such words will still be considered for further processing. And then make string of something here. So I'm just printing here by using make string in the last. And then value output is equal to, so counts are timed this time. These are the counts. And then println output. So basically it outputs this. It's totally this one. It will just print on the console with the time and how many counts have been processed. Then dropped counter values. So println how many dropped counter words have been processed. So these are the number of words which has been dropped. And then appending to output file absolute path. So this is just prints the file path. And then finally files.append of output plus slash n output file character set of default character set. So this way, I'm just returning the Spark streaming context instance, which actually comes back here, and then start method will be invoked on top of it. Finally, await termination method will be invoked. So the program will run forever and will wait for user to terminate manually. Okay, so that's pretty much about the program. So for any questions on this program before we go ahead and run this, Rehan says, is it similar to broadcast join in partitioned RDBMS? Actually, I'm not very sure in RDBMS how this works, but I can come back to you on this question, Rehan. Okay? Is that fine with you? Sure. Okay. So you understood this concept at least, right? So you can map it with your RDBMS skills. So Karthik says if await transfer termination is not used, the program is executed only once. No, not really. So this basically you have to stop the program in some manner, right? Maybe you can set some length also using this Spark streaming context instance. This is just like giving a stopping condition. I had to check if there is any other method in the Spark streaming context which basically allows you to stop the program after some number of days or after some interval. Okay, there should be some approach to do that. Maybe I'm not recalling that function name. Okay, Karthik. So then, so this is how do you determine blacklist values? So Satish, it's basically application dependent, right? So blacklist values is application dependent what you are trying to do. So that could be anything. Usually it will be like the terms, right, which are more frequently used terms like for, the, a. So these terms which does not really, I mean, again, it depends on your business logic totally. So if you want to predict the topic trends, for instance, then you might not want such kind of words to appear in your system because that's not a topic, right? That is not a topic. So you determine based on your business logic. Usually in data science projects, there is something called as stop words, which has some predetermined set of words. Okay, regular words used for grammatical purposes. Okay, so now that we are all clear on this program, let's go ahead and run this program, folks. So I have the program here. So bin/spark submit word count, recoverable word count, network word count. This I have to change this jar file name to hello spark, right? Hello spark underscore 2.1.jar. So localhost 999, and this is my HDFS path, and this is the file name. Okay. So I think there is no module 6 here, so let me change this. Let me remove this. Okay, so now the program will start and it will start writing the data. So arg.apache.dstream local class incompatible with the stream codec. Oh, okay. Failed to read the checkpoint from the directory. Hadoop fs-ls/user home embellizer. I'm just trying to check the directory path. Okay, I'm sorry guys. So let me do this. Let me change the path to some other path. Do fs // Okay, so I just started the program now with a different path because the previous path was having some issues. Okay, this requires some jar files. So there is something called as Google IO Extra, so I think I have to use this jar file. I can pass the jar files as well using this jars command. So comma separated list of local jars to include in the driver executor class paths. Okay, so let me supply these jars first. Now let me run it once again. Okay. Yeah. I have to start the Spark cluster. Because I think I'm running this program in the okay, excellent. Okay, so now we made it happen. So the program is running successfully now, guys. So now it just awaits for, okay, still some problem, is it? Oh, there is some other dependency as well. No such method. I think I have to search for a relevant jar for this. Let me check if I have a jar file here. Okay. So guys, give me a minute. So I'm trying to find out the right jar file for the Google. Yes, okay. So I'm using some external libraries for this program. Oh, okay. This is this Google. Okay, so this one is the different name. Okay, I understand now. So folks, I'm trying to find out the right jar. So for that, I'm just checking the Spark streaming libs. I suppose this guava.jar should be available in Hadoop. No. So this, whatever the debugging process, right, I'm trying to do, please pay your attention here. So it will be helpful for you in terms of debugging the issues and then fixing how it actually works. Okay. Yeah, it's here. This guy is here. I suppose this should work now. Let's check. Okay, so let me change the directory path now, because it would have actually changed it. So guys, hold on for a minute. Okay, so I think message for time being, it shouldn't be okay. Even though after changing the path, it is still complying the same thing. I think it should be fine. I think it's still okay. But let's try to run the program and see what happens here. Okay, I'll look into this issue offline. Okay, so we can come back. I'll execute this program probably the next week, folks. Okay, I'll take this offline. So any questions so far? So you conceptually you understood, right? So what's how it works, the Spark checkpointing process and all. Any questions out there? So Ajay says, are we okay? So Ram says, can you explain what is get or create? Okay, let me see what it is here, where it is here. So basically, what it is saying, what it means is, I'm passing the checkpoint directly to it, and then it just invokes this method, Ram. So this method is basically responsible to return the Spark streaming context instance. If it does not return, it can actually create with this checkpoint directory as well. Okay, so it is expecting from this method, so either get or it will create its own Spark streaming context instance. That's what streaming context at get or create. So it first invokes this method to get, otherwise it creates its own. Ram. Rajay says, are we eliminating the join or are we still using the join and improve the performance by copying the small files in our example to all data nodes? We are not eliminating the join, Ajay. So we are actually copying the small file into all the nodes. So this file, right? Actually, this is not a file here. I took that example just to explain in terms of joins, but this is an array and I'm actually caching this array using the broadcast variable. So in a way, I'm trying to do the join, and this join is basically like kind of a lookup join. So you see here in our program, where are we using that? So if you go and try to see here, so this right blacklist word dot value dot contains of word. So in a way, we are actually looking up into that array, which means essentially we are doing some kind of join operation here. It's not really a join operation, but it is a lookup operation. But essentially, it is analogous to join here, Ajay. So we are using that after putting it into the distributed cache, Ajay. Okay, no problem, Anand. Uh, you have any questions there? Then Ajay says, when we import the source files from the example, you are showing, will it have all the jar files required? So, or we have to follow your recording to get them. Oh, okay. So when you run this in your example, so probably it will not have, it will have actually, the jar files will have in the Hadoop. So as I just shown you, right, it is in the Hadoop class path. So you have to go to Hadoop to actually pass the jar file. Otherwise, you can download it from internet also, Ajay, that gava.jar file. I can otherwise copy it to you, so that will be more meaningful for you, right? Let me copy this command to all of you. You can use this command to retrieve the jar file. Okay, is it fine? So yeah, so let's come back a little bit and then let's move on to the another topic here, which is MLA package. Are we all clear so far? Any questions, Ajay, Anand, or anyone else? Sure, Ajay, no problem. Excellent. Okay, so let's move on to very one of the core concepts within Spark, which is MLlib package. Okay, let's just come back a little bit and just think from a fresh mind from here onwards, because this is nothing to do with Spark streaming, at least for this concepts as of this concepts are concerned. So just think freshly, and we have to now start thinking as if we are a data scientist. Okay, because Spark streaming module is been designed for handling the data mining kind of requirements for in any applications on large volumes of data. Okay, so let's try to get some basic introduction out of it, folks. MLlib is Spark's machine learning library. So MLlib basically is a module within Spark which has the implementations for the most popular machine learning algorithms used widely across the industries. Okay, it has got pretty much the popular algorithms available as of today in Spark, and this package is evolving quite drastically, so you might find a lot more algorithms being implemented soon. And having said that, this package has been integrated with R, you can run certain functionality in R directly on top of Spark. So if you run some functions in R, those functions will be executed on Spark. Okay, so it has got support for both. It essentially does not mean that all the functions in R could run on Spark. There are some very primitive functions which could still be executed on top of Spark, but not all of them. Okay, and then coming back, it has got its own algorithms as well. So you does not have to leverage on R specifically to run the algorithms, even though it supports R integration with Spark. Okay, and there is actually a new module called as ML module. So there are two different modules now. MLlib is one package, ML is one package. So now most of the development is actually happening on ML package. Especially this package basically is an abstraction for the R kind of syntax. So they are trying to pretty much synchronize the syntax with R so that the R programmers could easily learn the Spark framework as well. Okay, so it consists of common learning algorithms, as I just said, and it has got two different packages, MLlib and ML packages both. The key differences between these two packages. When we are talking about MLlib package, mostly the data structure abstraction is an RDD. But when we are referring to ML package, this ML package is designed around a core data structure within R called as data frame. If you know about R programming language, R environment, statistical environment, in R, one of the core data structures is basically referred as data frame. Data frame is just nothing but a kind of table with some columns and rows. You could do miracles out of the data frames. It's quite easier for you to run some complex functions on a table using the data frame abstraction within R. Similarly, in Spark, we have now come up with the concept of data frame, where most of the machine learning development is happening around this particular data structure, data frame, and within the module ML. Okay, even though still we are on the MLlib package, sooner ML will evolve, and probably it can replace MLlib package totally. Okay. That's kind of a bit crisp introduction about MLlib package within R, so within Spark. So let's get into the deeper understanding of what kind of algorithms are available and all that stuff. So Bishwajit says, what are the differences between Apache Mahout and MLlib? That's a very good question. Okay. Apache Mahout framework is the machine learning package available within Hadoop ecosystem. Okay, it runs purely on MapReduce. Nowadays, in the latest versions of Mahout, they are trying to integrate it with Spark as well, and they have been successful as well in integrating with Spark. So you can run some algorithms in Mahout directly on Spark with the Spark integration with Mahout. Having said that, Mahout framework is originated. It's a Java framework. Its roots are from another language, another framework called as Lucene. Lucene is a search and indexing framework available in Apache community. It's an efficient, it's a very interesting tool for implementing the search and indexing on any type of data you can talk about or you could imagine. Okay. So Apache Mahout is inherited from that package and also been inherited from MapReduce point of view. So with which it gains most of its functionality from Lucene, with which you can easily do the indexing and searching of the data. So text mining is quite easier using Mahout versus MLlib, mainly focused on running or implementing the algorithms using the in-memory kind of implementation, where the performance is the key driving factor for MLlib. Even though you could see redundant algorithms in both Mahout and then MLlib packages, how they run internally is quite different. Mahout uses traditional MapReduce mainly behind the scenes. MR framework to run the applications in memory, with which it gains huge amount of performance compared to that of Mahout framework. Technically, there are some pros in Mahout, okay, and such functions are not available in Spark. You have to leverage on some third-party frameworks in order to build such kind of functionality in Spark. Even the Spark is kind of bit early, still it is in early stages. It takes a lot of time to be evolved to that to compete with such kind of frameworks like Mahout. Okay, does that make sense? I think we have spent enough of time over there. So if I come back a little bit on Spark, so here are different types of algorithms and statistical functions available as of today. This list is not the finalized list. However, since the list is growing, maybe at the point in time when I have created this slide, at the time this should be fine. Okay, but anyhow, this is not. There are plenty of other algorithms now within the Spark MLlib package. You can see Spark has its own data types. Then basic statistics you can perform so easily using summary of statistics, correlations, sampling, hypothesis testing, random data generation. These are some of the basic statistical functionality which you could easily run within Spark framework. And coming back to algorithms point of view, so we have got both regression and classification algorithms. So as in linear models like SVM, logistic regression, and linear regression. So basically linear regression and logistic regression both fall under regression techniques. SVM is a classification model. Then Naive-based decision trees and ensemble of trees, all these three fall under, again, classification techniques, folks. Then collaborative filtering basically is under the recommendations set kind of algorithms. Alternating least squares is one of the implementations under the collaborative filtering. Clustering, you got like k-means, Gaussian mixture, and power iteration. These are some of the clustering algorithms. Dimensionality reduction to reduce the size. Basically, you got singular value decomposition and then PCA, principal component analysis. Then feature extraction and transformation and optimization. So these are stochastic gradient descent. SGD is one of the algorithms, and then BFGS and LBFGS are some of the implementations available as of today. So even before going further, Since we are in ML module, so let's spend some time understanding some of the basic statistical terminology before we go and really understand about any algorithm within the ML package, folks. So let me start with the summary of statistics. So when you say summary, so basically what does it contain? So usually like summary can contain mean, median, mode, then standard deviation, variance. So these are some of the basic statistical functions or statistical terms under the summary, folks. So do you all understand what mean, median, mode, ST and variance stands for? Or would you like me to explain in detail about this? Say yes or no. If you want me to explain, say yes, otherwise no. So I can see mixed answer. So let me at least try to quickly explain, at least to which will help few of those who are actually interested. So mean basically is like, let's say if you have a set of elements, let's say 4, 5, 6, what is the mean for this? It's basically 1 plus sum of all the elements, 1 plus 4 plus 6 divided by 3, right? This will give you mean. And then median. So let's say median. What is median? Let's say if I've got elements like 1, 2, 3, 4, 5, 6. Median in this is 1, 2, 3, 4, 5, 6. So there are 6 elements. Let's say if there are 7 elements here, the median will be 4. Okay, the element which is in the center is treated as median. However, if it is just 6 elements, then you just do the mean of the both the elements here. 3 plus 4 divided by 2 will become the median. Mode basically is like, if there is some repeated element in your set, so whichever the element is repeated the most is called as mode. Standard deviation, so basically this is another statistical term. So let me explain that by explaining about the variance first. So in order to explain variance, I would say, let's say you have got two-dimensional plane, x-axis and y-axis. So if the points in this x-axis and y-axis are distributed something like this, so these points could be anything. Like for example, if you are measuring the ranks, I mean if you are actually spotting the ranks of each student on a two-dimensional plane. Okay, let's say x-axis as in the actual for instance, x-axis could be the actual marks being attained, and then y-axis could be the number of students. Okay, so then if you map let's say the points, like how many number of students has attained how many marks, so basically the a graph would look something like this. And if you draw a line meeting most of the points in this two-dimensional plane, then the difference here, right? So the difference here of this point versus this median here. So you just compute the differences. You can do the average of all these differences, and that average will become your variance. Okay. So the average of all these differences of all the points versus this median would become the variance, and then the standard deviation could be computed using the variance, folks. Is it clear, Karthik and Rehan? There is a formula though, so let me just check the formula. I can't recall the formula, so let me do that. So it is the summation, right? As I told you, it is the summation of all the differences basically. So this mean. So variance is basically the summation of all the differences. So if you compute the differences like this, the average of all such differences, squared differences, will be your variance. And the standard deviation is just like square root of variance will become your standard deviation. So square root of the variance is a ST. Okay, so that's what all the statistical terms mean. So other than that, there are some more things as well, like normal distribution and asymmetric normal distribution. In a normal distribution, if you have to consider a particular set of elements are in a normal distribution, mode will be at the same point. So let's say normal distribution. If I go to images, there will be some images for this. So it will be in a bell-shaped form, and then let's take this image. This is quite interesting. So all three, mean, median, mode, exist at the same point. Then you can say that the distribution of the points are in symmetric normal distribution. So there will be asymmetric normal distribution as well. In asymmetric normal distribution, the bell shape will be either slightly towards its left or towards its right, depending upon the skewness of the data. Okay, if the data is left skewed, and the bell shape will be towards the left. Otherwise, if it is in the right skewed, then the data will be towards the right. So then if I say asymmetric normal distribution, okay, you can see here. So mode is at some point, median is at some point, and then I think this may not be quite interesting. Okay, this will be quite interesting, folks. So mode, median, and mean are existing at different points. So this is left skewed data, by the way. There could be right skewness as well. So where this bell shape could be slightly towards the right. Okay, so these are some of the statistical features which you could compute as part of the summary. And then classification and regression. So this should be quite interesting to all of you. So let me spend some time to explain about it. So at a very high level, right, in statistical modeling or in data mining world, basically you can classify the algorithms into two different categories. So those categories include one is basically like classification algorithms, and then the clustering algorithms. Classification algorithms and then clustering algorithms. So let me define about them. So the difference between these type of algorithms, right, classification and clustering techniques. So when we talk about clustering algorithms, so in clustering algorithms, you may not have to have a value associated with it. You may not have to have a label associated with your training dataset. So such kind of algorithms which does not require a label to your training feed will be considered as clustering algorithms. And then classification algorithms usually are like they have a label associated with them. So such algorithms are called as classification algorithms. So I think most of you may not have understood about this concept. Let me explain it with some example. let's say for instance, if you understand, right? Human beings are basically we are very good in identifying the patterns within the data. So human mind itself is designed in such a way, for every decision you make, you basically are trying to create some patterns within your own mind, maybe without your notice. You're actually trying to justify any decision by looking at some previous patterns or your experience. Okay, that's why human beings are considered as pattern-seeking beasts. Not only human beings, most of the animals does the pattern finding as well. Okay, but they actually does some pattern analysis as well. So to explain it in a lower terminology, I mean in simple terms, let's say if you have a 1.5 1-year-old kid, or maybe 1.5 year-old kid, or maybe 2 years old kid. So if you take a 2 years old kid to a parking lot, for instance, let's assume that the parking lot is quite big and there are too many vehicles of different types have been parked in your parking lot. So this kid who is actually watching the parking lot, he may not know the vehicle name, in the sense he may not know whether it's called as a bike, whether it's called as a car, or whether it's called as a truck. Even though he does not know these terms, he will still be able to group the vehicles within the parking lot into separate categories. Like he can be able to actually group the bikes into one category, he can be able to group trucks into one category, and then he can be able to group cars into one category. So what he is essentially doing is, he does not have any idea of what this has been called. So the training dataset does not have any labels, but by looking at the similarities within the given dataset, he is trying to group the elements into different categories. So this kind of problems, which does not necessarily involve a label associated with it, but just we learn of our own and trying to come up with some groupings based on certain properties, certain features, is called as clustering algorithms. Okay, and then basically classification algorithms are basically something like say with labels. Let's say if I give you some set of images, some images with lion images, and I give it as lion, and then some images with say elephant images, and I'll tell you specifically, okay, these are elephants. So then you actually process those images with the labels. Okay, this kind of image is called as lion, and this image is called as elephant. And then if I give you another image and I'll ask you to classify it, since you know, okay, how the lion looks like, so you can say that, okay, this could be a lion or this could be an elephant, because you are actually doing the classification based on your previous training data set and based on the features and based on the hypothesis being created. Okay, so these are two high-level types of algorithms. However, there are multiple other types, even regression models, for instance. They could be actually considered under the classification, depends on the type of regression you are trying to apply. Either it's logistic regression or linear regression. So both these models are regression techniques, and then recommendations algorithms, which are basically referred as collaborative filtering algorithms, folks, models. Okay. So these are some of the fundamentals, and you can see like for classification techniques, as I told you, SVM is one of the classification example. In fact, you can still consider this regression techniques under classification too. Navy Bayes, decision trees, and then ensemble of trees. So these are all, in a way, they all fall under classification algorithms. For clustering algorithms, we have got k-means clustering algorithm, Gaussian mixture, power iteration. These are some of the examples for clustering techniques. And under collaborative filtering, we have got implementation for alternating least squares. So basically for collaborative filtering, correlations are used pretty much in the collaborative filtering kind of algorithms, where you try to come up with the recommendations algorithms, folks. So we can discuss about correlations in a moment when we actually discuss about our project work now, mini project for now. Okay, sampling you all understand. Basically, sampling is nothing but in a given big corpus of data, you just pick some random samples which meet most of your conditions. Based on that, you do the testing of your model. And then say hypothesis testing. How many of you understand what is hypothesis? Say yes if you understand. Say no if you don't understand what is hypothesis stands for. The term probably many of you might be familiar, but most of you may not have the context of what actually hypothesis stand for. Okay, so I think there are like 50-50 ratio I can see. 50% of the participants, they know about it, and 50% may not be aware of it. Okay, let me take a quick example to explain what is hypothesis in my own way. So in simple terms, right, to explain about hypothesis. Okay, guys, so let me take a very one simple example to explain this situation here. Let's say if I give you a if I ask you a question. So let's say you are starting to your office by 9:15 a.m. in the morning, and I ask you a question. So how much time it would take for you to reach office? Let's say if we have got two buckets here, one is 15 minutes bucket, and let's say one is 30 minutes bucket. Don't say I'm in Bangalore, so it could take hours. I can understand the situation. Or I'm in Delhi, it might take 3-4 hours. Okay, so just ignore it for time being. Okay, independent of your location, let's assume we got two different buckets. One is like 15 minutes and 30 minutes bucket. If I ask you this question, so what would be your answer, folks? Typically, your answer will depend upon some parameters. Okay, I would imagine like this. So the time you start to your office, that would really make sense. That's one of the key features, right? And the traffic at that point in time, this is another feature. Let's say maybe there could be some other impacting features also. Let's say there is a rain, which could impact your time as well, right? Time to reach your office. And let's say some other features, for example, what could be additional factors which could impact your time basically to reach to the office. Could you give me some more examples here, some more features? All right, let's say accidents, correct. Let's say accidents, okay. We can even generalize this, let's say based on events, but okay, let's be specific as accident, and then probably the route. Okay, so these are some of the key features, right, which basically determine what could be your possible outcome. Okay, these are the driving factors for this. Let's see if I have to fall into this bucket of 15 minutes. My hypothesis would look something like this. I could come up with an hypothesis to be able to tell that I can reach in 15 minutes. Even you do the same thing, right? If I ask you whether you could reach the office in 15 minutes, you will actually come up with some hypothesis. Maybe without your notice, you even don't know that you are actually finding out the hypothesis. And where does the hypothesis come from? It's from your previous experience with some training data set in our case. Okay, the hypothesis will be derived from the training data set. In our case, in this example case, it will be from our experience. Let's say you have been going to your office since 1 year, so you know the patterns better than any other. Okay, you could tell me easily that, okay, I can reach in 15 minutes. I may not reach in 15 minutes. So how does the hypothesis will look like in this case? Is basically something like this. If the time you start falls under say 9:15 to somewhere around 10. Probably you might reach within 15 minutes. Just assume like this. Okay, or maybe this is a kind of peak time, right? Let's say 8:15 to 9. That would be easier. So 8:15 to 9 probably unlikely is considered as non-peak time. And then traffic. If the traffic is so high, it's a traffic is average. Typically, our traffic depends on the time also, right? So time you start basically. If there is no rain, okay, then you can say, okay, there is no rain and there is traffic is average, and if I'm starting in this time period and then there are no accidents, then the route is the regular route. Okay, then with this hypothesis in your mind, you could tell me that you can reach within 15 minutes. So hypothesis is just not about it. Okay, so you actually construct such kind of many more examples for 15 minutes. So that is one example. And even though the traffic, let's say the traffic is low, even though there is rain, if the traffic is low, you can still reach in 15 minutes, right? So let's consider that analysis. So you are essentially constructing some possible cases here and cumulative all these examples, right? So if you can actually construct a more generic kind of hypothesis out of all your examples here. So these are, let's say these are instances with which you are able to tell this. However, you can make a generalized hypothesis in your mind. So that generalized hypothesis would look something like this. If the time start falls between this timeline, let's say 8 to 9, and then let's say the traffic could be probably say some kind of average or low, other than it should not be high. So I'm just trying to make it generalized rather than very specific examples here. I'm just making it very generalized so that all these conditions will be met. All these different examples will be, these are like a training data set for us. Okay, this is one instance, one occurrence, and this is another occurrence. So out of which I'm trying to generalize it. Okay, and then let's say this should not be this. Okay, accidents. The third parameter, right? So third parameter should not be. There should not be any accidents. Accidents should be nil. Okay, and then route should be regular. So this is a more generic one, right? So you can substitute this example, this match. If you substitute this example, this will also match. Let's say if there is another example, something like this. Okay, another example could be high here. So this will not match with your hypothesis here. So this I refer it as hypothesis, which you are trying to form in your mind. And based on your hypothesis, you can easily determine, okay, considering there are two possible outcomes here, right? There could be n possible outcomes. Depending on that, your hypothesis will differ, how many hypotheses you create by yourself. So in this hypothesis, considering there are two outcomes, you can actually substitute any of these instances and you can get the actual result. So if you substitute both of this here, you can say within 15 minutes. If you substitute this, since there is no condition matching, so you can say it will not be 15 minutes, so it is 30 minutes. Okay, is it clear, everyone who are even not familiar with statistics? I hope this is very in simple language, right? So we try to understand everything in a simple language here, and which also helps. Basically, simple is better. Complex things could sound a bit exciting, but may not be helpful. Okay, may not always be helpful. Are we good so far? Say yes or no quickly, so we can proceed further. Excellent. I think pretty much everyone is good so far. So even smiley should work, folks. Okay, I'm sure you guys are accumulating too many things, so it's better to just be casual so that you're not applying any pressure on understanding things. Okay, so on top of this, let's move on and try to understand the typical steps involved in a data science project. Okay, then after understanding that, we'll go back and we'll see what kind of supporting supporting concepts within Spark available to us to implement the data science project. And then we go ahead and actually work on a real-time example, folks. Okay, so in a typical data science project, what happens is these are the common steps usually a data scientist will perform. Okay, featureization, it's also sometimes referred as vectorization, training, model evaluation, and then okay, so these are three key steps, right? So one is featureization, training, and then model evaluation. These are three key steps involved in a data science project. So what you do in the featureization or vectorization step is basically you get a raw data set, which is referred as, let's say, very pure, in a pure raw form of the data. What you have to do, you have to make sure that the data is in such a way that your algorithm can understand. Whichever the algorithm you pick, whichever the model you pick for your problem statement, you have to first prepare your data in such a way the model could consume. When I say model, I'm actually referring to any algorithm, okay, in statistical terminology. So what will typically a data scientist do to actually prepare the data? He can run some SQL queries, or he can depend on the data engineers like us who can actually help them building the data out of it. In the real world, the way it works is the data scientist who actually comes from mathematical statistical background, he actually decides what kind of model he would like to implement depending on the problem statement. He's the one who decides which data set is required and in what form. Then data engineers like us, for example, could actually help a data scientist in organizing or in preparing the data. If it is simple, like in SQL and all, probably he can take care of himself. But if it is complex, if the data is purely in raw form, if we have to write some MapReduce jobs to actually prepare the data, then he has to obviously fall back on us. So then we start preparing the data. So this, in a way, we are actually participating in the featureization process as well. So where we are from the raw data, we extract some data and we aggregate and we actually generate the data in the finest form, from which the data scientist can take on and he can create the vectors out of it, which are basically ready to be consumed by any model. So once he generates the vectors, so typically a vectors will contain features like this and the possible outcome. Okay, depending on the type of algorithm, again, the features and then the possible outcome of that value of that particular instance of training data. So that's called as feature vectors. So once he generates the feature vectors, then he start the training phase. Okay, he may probably separate the data into 20-80 ratio, and then he can use the 80% of the data for training his model. So once he trains his model, essentially he's generating a hypothesis, which is, in technical terms, he is actually creating a binary program. That binary program is equal to the hypothesis just now we discussed, which actually help us labeling the new examples. Okay, by looking at the existing training data set, it will create its own model. So once the model is generated, in the training phase. Then that model will be evaluated. So you can actually test the performance of the model. So there will be different testing methodologies applied depending on the different type of algorithm. If it is classification, if it is specific algorithm, you have specific type of testing methods with which you evaluate the model. So essentially, like, he can actually use that remaining 20% data to do the actual predictions. Can actually compare the performance of the predicted outcomes versus the actual labels, with which he can test the algorithm. He can say with some confidence that, okay, this is the confidence level of my model, with which he can go on to production or not. If this does not work out, probably he can try to tune the data, he can try to tune the parameters, he can try to tune the models, change the models, and try out different approaches to come up with the best model. So these are typical steps involved in a data science project. If I come back a little bit to the previous slide, it says data frame, transformer, estimator, pipeline, and parameter. So these are different terms used in Spark which actually help us in preparing a data science project like this. Data frame as in the table, right? You can actually quickly process the data using the data frame. Transformer as in it will actually is an algorithm to transform one data frame to another data frame. Estimator as in like which actually comes up with the predictions out of your data frame. And then say pipeline as in you can actually pipeline the transformers and estimators together to cook up the entire data science project. And then say parameters as in it could be all transformers and estimators now can share common APIs and specifying parameters to it. So that's a quick and a brief introduction about the statistics, and then data science project, how it basically looks like, and about the Spark ML package and an ML package. Are we all good so far? Any questions? Are we all good? Excellent. Sure. So let's move on here and let's try to understand about a project here, folks. Okay. Recommendations engine project discussion. So now what I'm going to do is I will run a mini project now. Okay. And in this mini project, I'll first walk you through the problem statement. Okay. And then we'll go ahead and run the algorithm model on top of it. Recommendations engine at IMDb. So basically, what I'm trying to build is a movie recommender platform, movie recommendations engine. Okay, in which we actually I have actually downloaded some real world data where you have got the real users with user ID, item ID, and then the preference level and the timestamp at which that particular preference has been given. Data downloaded from third-party website. I'll show you the link as well, so that if required, you guys can download other data sets as well from that link. Okay, it does not only have this particular data set, it also has so many other data sets which are really good for recommendations kind of problems. Okay, for evaluating recommendation algorithms. So in this case, let's consider this is as our data. This is the problem statement, right? So we are actually building a movie recommendations engine. So typically in a recommendations engine, there are different types of algorithms. Let me just explain quickly. Typically, we call recommendations as collaborative filtering. So when I say collaborative filtering, essentially I'm referring to recommendations platform, recommendations algorithms, guys, when I say collaborative filtering. So under collaborative filtering, there are two categories. Okay, there are two categories. One is basically Okay, so let me even do this. So under recommendations, right, there are mainly two categories. One is collaborative filtering and the other one is content-based filtering. Content-based filtering under recommendations. So either one of them, when you say content-based filtering, when you say collaborative filtering, you are essentially referring to recommendation algorithms. These are two top categories under recommendations engine. So under collaborative filtering, again, you have got two types of models. So one is basically user-based recommendations, and the other one is item-based recommendations. These are two categories of algorithms. And content-based algorithm is just one. I'll explain all these three together quickly with some sample data. Okay, let's say what I will try to do now is basically I'm trying to explain the user-based recommendations. So user-based recommendations. So since we are going to implement the recommendations example, it is essential for us to understand at least some basics of user-based and basics of recommendation algorithms, right? So that it would be intuitive for us when we actually go ahead and write the program by itself. So what happens is in user-based recommendations, let's say I have some users. Okay, let me take 3 users here. And then let's take some movies on the right hand side. Okay, the movie names as in like let's say In Time is one movie, and let's say iRobo. Okay, and even let's call it as say Iron Man. Something like this, right? So some movies I'm trying to take. And then let's say some another movie, let's say Expandables. On the other hand side also I'll take some users as well. So user side I'll take few names. Let's say Karthik, then say Bishwajit. Sorry if the name is not properly written here. Okay, if I'm written some typos here. Let's say Anand. Okay, so 3 users are there, and let me take another user also. Yeah. Let's say some users I'm just taking randomly, you know. So now that if there are some users and there are some movies like this, let's say if the user Karthik has actually seen the movie In Time and he liked it a lot, and let's say he also seen the movie and liked it a lot, and also assume that he has seen the Expandables and liked this movie a lot. Okay. On the other hand, let's pick up the another set here. Say Bishwajit also seen this movie and he liked it, and then he also seen this movie and he liked it as well. So let's say he also seen this movie and liked it. Maybe Anand also has seen some movies. Probably I have to take different colors to make it more intuitive. Okay, so let's say he has also watched this movie, and then he also watched this movie, and then he also has watched this movie. Okay, if you take this data set, right, existing data set here, if I have to recommend a movie to Karthik, for instance, I could actually do this. So let me even take some more data to explain it in a better way. Then let's say Rezi has seen all 4 movies and he has liked all of them. So let's say if I have to recommend a movie to Karthik now by looking at this data set, could you guys tell me which movie I could recommend to Karthik? Of course, here there is only one more movie. Let me take another movie. You guys can say that, okay, sir, there is no only one movie is there, so obviously I can recommend that movie to him. But let's take another movie here. Let's say Titanic, for instance. This kind of data set, right? So which movie you would like to recommend if it is user-based recommendations? First of all, what I would like to do in user-based recommendations, I will try to compile similar users like Karthik. Okay, with similar behavior like Karthik. So whom all I can actually say that very close to Karthik by looking at this data. I can say Reggie is very close because he has actually seen all the movies like Karthik did and he also liked similarly. And then also I can say Anand has liked it, and then Bishwajit. So I can say Reggie as the top priority, second as Bishwajit, and third as Anand. So these are 3 similar users like Karthik. So of course you guys can say only the data set shows like only, let's say Shakti has only seen this movie and he liked only Titanic. Maybe he has seen Iron Man, but he didn't like it for some reason. Okay, possibly he might like it, but let's say he did not like that movie. Okay, let me just draw something with a dotted line or something like that. Let's assume that he didn't like this movie. So by looking at this data, so I could easily say that okay, there are three matching users to Karthik, and the most matching user is Rezi, and Rezi has seen iRobo and he liked it a lot. So now I can recommend Karthik to watch Rezi. Sorry, to watch Robo. So iRobo, so he can actually go ahead and watch this movie, right? So this is based on user similarities. I mean, based on users, you are trying to do the recommendations. So such recommendations are called as user-based recommendations. On the other hand, item-based recommendations. So is basically you compute the similar items here. Let's say in this movie, the similar items are In Time, iRobo, and Iron Man. These 3 could be similar movies because okay, so similarities will again be computed by users only, folks. Okay, based on users watching behavior, similarities will be computed for the users, and you do item-based recommendations rather than user-based recommendations. Now, once you group, let's say similar items like In Time, iRobo, and Iron Man together based on the similarities in the movies. So then you recommend Karthik to watch the iRobo. Rather than computing the user similarities here, you compute the item similarities and recommend based on the items. So this is something called as item-based recommendations. And finally, last but not the least, content-based filtering. Okay, so before going there, so usually user-based recommendations are quite not stable, in the sense that user preferences will change over a period of time. So if you are leveraging on user-based recommendations, then you have to really recompute those recommendations again and again and again and again every time, because users' preferences keep changing all the time. But if you go with item-based recommendations, it is somewhat stable and constant in nature. So they won't change, right? User item similarities won't change just like that, just like user preferences. So in that case, if you're going with item-based recommendations, you don't need to frequently refresh or rebuild your model. Okay, rather you can just build it once, and then maybe after a long interval, you can actually recompute the item similarities as well. However, the concept you understood, right? What is user-based and what is item-based recommendations and the difference. So finally, content-based recommendation is something very simple. So basically, let's say in the content-based recommendations, if you have 3 different movies here, let's take another 2 movies to this corpus. let's say Sherlock Holmes, and then let's say another movie, for instance, Captain America. So if the corpus is like this, content-based filtering, what it says is basically it finds out the actual content within the movies. Content in the sense it could basically look at the director in the movies, or maybe can look at the hero in that movies, the top lead actor in the movies and all. For example, if you look at this corpus, Iron Man, Sherlock Holmes, and Captain America. So the lead actor in this is Robert Downey, for instance. So if let's say if Karthik has, if Reggie has watched iRobo and Iron Man, sorry, both this, let's say Iron Man, and he also watched Sherlock Holmes and he has given rating. So by just looking at this data, without even looking at the item similarities, without looking at the user similarities, we can still recommend Reggie. Because in Reggie's movies he has rated, we can see some pattern. So that pattern is basically like in both the movies there is one lead actor, he is common in nature. So the next time when if there is another movie with the same lead actor, you can actually recommend that movie as well. So in this case you don't need to really compute any models as such. Even a simple SQL program which can actually find out this kind of patterns, you could be able to still do the recommendations. And this content-based filtering is also very good. It works pretty well, simple. It works pretty well for most of the use cases, especially if you don't have any historical data to be able to compute item-based or user-based similarities. Okay? Are we good, guys? Are you all following with me, or are you lost somewhere? Anand says Python or Scala, which is better for ML. So actually my recommendation, I can't actually recommend either one of them, but usually Python is more mature than that of Scala, but Scala is more scientific library. So nowadays both are considered equally important. It mostly depends on which language you are comfortable or familiar with, Anand. Okay, in terms of Python, Python has got many implementations, right? It has got different packages by itself. Python, it has evolved a lot for machine learning, but Scala is also picking up, so both are okay, good. Then Rehan says, could content based be identified as sci-fi movie and adventure? Yes, of course, it can be done in that manner also. Like let's say if you want to say based on the genre of the movies, you can still do that. Okay, it's also a content only, right? You already know the genre of the movie, and we are just recommending based on the genre. That's it. Any libraries in Java? So yes, of course, Mahout is one of the libraries as well, but there could be some others as well. Like for instance, there are for specific models, there are like libraries. For artificial neural networks, there is a package. So there are different packages for different algorithms as well. Anand. Okay, so I think now everyone is now quite clear, right, on what we are talking about and what is the problem statement. Okay, so let's talk about the design perspective. In the design perspective, how the solution should look like. The solution should look something like this here. So essentially, to handle this movie recommendations platform, so you have a data source. So first, any algorithm, so any recommendations engine or any algorithm as such, typically, it will have a data source. I mean, from where you get the data. You should decide on the storage, and then the computing engine, and then the final dashboard. Okay, so these are key components, are a cheat sheet for implementing implementing any data science project, right? So in terms of design, not really in terms of activities, but in terms of design, what should be the key components. So in the design, how you actually select the data source, it depends, right? In any applications, the data could reside in databases like RDBMSs. Data could be in NoSQL databases like Cassandra, RAC, Neo4j, Redis, MongoDB. All these are different databases. So data could be on NoSQL databases. Data could be on some text files, CSV format or Excel files. It could be any format. So no matter what type of data or where it's been stored, still you can consider Hadoop as a storage system, especially considering two factors here. One, if the volume of the data is quite high. The other, if you're getting multiple feeds from different sources and somehow you want to aggregate the data, just go with Hadoop. Hadoop actually offers a better file system, which is distributed file system, allows you to handle different types of data very efficiently. So just choose Hadoop for storing the data. And of course, it depends upon what kind of SLAs and total data flow altogether. You have to select the technologies. However, for this use case, Hadoop will be relevant choice for us. The next thing, you could actually use Mahout to solve this problem as well. Mahout has got a beautiful machine learning algorithms for recommendations engine. Okay, it has got a all set of recommendation algorithms and recommendations package in Mahout. However, let's assume that our requirement is something like you need to process you need to build the model quite in a real time. Okay, at least very fast. It should be highly performance oriented. If these are some kind of features which you are looking for, then better go with Spark MLA package, which is quite efficient in terms of performance, and in fact it can even do the building of the model in real time as well. Okay, because of its underlying built-in capabilities are stitched together because of different modules and all, right? So our choice, our preference will be Spark, especially because it offers the in-memory cluster computing capabilities. And you choose the MLA package just because it has got the machine learning library and implementation for machine learning algorithms, includes recommendation algorithms as well, which is ALS, alternating least squares, is one of the implementations for recommendations algorithm. Okay, so now that we understood the design typically, so now let's go back and first try to look at the data, understand the features within the data, and we go through the program, and then we run the application on that data set, folks. Okay, now I'm going back to my VM to show you how the data would look like. So I'm just logging into Mahout directory where I have kept the data. Okay, so CD week 45, for instance. So ML100K, this is basically 100,000 users. I think 100,000 preferences actually. Okay, there is a file called ua.base. Let's see, viua.base. If I say this, see here, this is user ID, this is item ID, and this is the preference of the user ID, rating. User ID, item ID, rating, and then this is timestamp. This is the data set, folks. And there are so many users like this. I think there are 1,000 users. And then there are 100,000 recommendations, folks. Okay, see here. This is the data set available with us for implementing the movie recommendations platform. Okay, so now that we have the data and we understood the data, let me walk you through the program. So if I go back to the program, movie.scala. So in the movie.scala, I've got movie lens ALS, alternating least squares. I've defined main method here. If you look at the package, also pretty much in Spark MLib recommendations ALS, and then rating, and then remaining are pretty much the same same classes and APIs. So movie lens ALS main method, Spark conf set application name as movie lens, and then Spark master as localhost. Then Spark context, which is pretty much familiar, and then text file. So you just pass the text file path here. So let me change this path. and then this is the input data set, and then raw data dot map of, I'm just splitting it by /t, taking first 3 columns, and then raw ratings, and then raw ratings dot map of user movie ratings. I'm just creating a structure like user movie and then rating. So after I create the structure, als dot train off. So this train method, so als is the algorithm. Train method basically takes the ratings and then will compute the model. So once it generates the model, it takes some additional parameters also, like this here. So one is basically number of iterations, and then this is some percentage. I have to actually check the parameters here by looking into the function signature to be able to tell you. And however, let's assume that these are number of iterations, and these are maybe the top 5 matching users, and then this is the ratio of the matching. Then users features that count. So once I get the model, so user features that count, product features that count, and then predict rating. So model that predict off. So I'm predicting the rating for this particular user 789. So 789 user, then value is equal to 10. Top 10 recommendations for this user 789 is this one. Okay, so I'm just printing the top 10 recommendations for this user 89 ID. So then I'm again reading the data. So movies that map of a split of pipe. So using pipe symbol, I'm splitting the data, slash and pipe. Then take to map of array. So again the same thing. So titles of 123. So this is an user.item. So let me see what that file contains. u.item. So this contains some pipe here. So 8 pipe, some information here, like movie name, I think. So movie name, year of release, and then this is the link of that movie, which gives the details of that movie. So Dead Man Walking, these are the movie names, right? So I'm just retrieving the movie names possibly here, and then I'm getting the titles out of it. So after I get the titles, I'm just based on the ratings of this user 789. I'm assigning the movie names for this guy, and then sorting by the top ratings, and then printing it onto the console. Recommended movie is the first movie. So this is the movie recommended for this user 789. Okay, is it clear? Guys, any questions? So you guys can try this out once you get the code. You guys try it out. If you have any questions, you guys can ask me in the next class, next session. Shall I proceed with executing this program? Okay, so now I'll build this program quickly. Let me check if this program has already been, I don't think it's been built, so I have to build it now. The project name is Scala Test Project. Okay, so Ram wants it to be explained once again. No problem, Ram. So Ram, okay, so this is clear, right? So I'm just importing some APIs here. What I'm trying to do here is I'm instantiating configuration instance and Spark config instance, Spark context instance. This is clear, I hope. And then I'm actually I'm creating an RDD out of this u.data file. Okay, what does this u.data contains? User ID, item ID, and rating. So once I read this, I'm splitting with tab space. So if you look at this data, u.data here, so via ua.base, this is tab separated file, and I'm splitting that with tab space and taking first three columns, because this has four columns and the fourth column is timestamp. Guys, are you able to hear me? Say yes or no. Folks, are you able to hear me? Is it clear? Okay, so Shakti, it looks like there should be some problem from your side, so please try to reconnect to the session, Shakti. Okay. Okay, so are you all following me so far? So I'm just splitting the records with tab space and taking the first three columns out of it. And then raw ratings that map off. So I'm trying to map the raw ratings, okay, to an array of user, movie, and rating. I'm converting the types to int, and rating, okay, because all these three are integers only. So once I create an array out of it, then this is the ratings here. As I told you, there are three phases, right? One is data prep phase. Data prep phase is done here. Preparation is done. Now training phase, which is modeling phase. For training phase, I'm using this ALS model, alternating least squares, that train. This method will actually build the model by using this data. Will generate the hypothesis, which is basically the model. Model is a binary program, which is the hypothesis, which is outcome based on the training done on the training data set. Okay. Once I get the model is the one which will help us in predicting the new or unseen instances. Okay, let's say if I want to recommend you okay, a specific movie, then I can actually pass your ID so that it will recommend, the model will recommend me some movies based on previous training datasets. So what I'm trying to do is model.predict of 789 and 123. So what this guy does, predict method, is basically predicting the recommendations for the user ID 789 and 123. So I get the predicted rating for this user 789, and then user ID 789, and then value k is equal to 10. Basically I want to filter out top 10 ratings for this user because I have already predicted the movies. So the top movies predicted would be like something like say Titanic or say iRobo, something like this. The model has predicted movies for this user ID 789. And then recommended products. So when I actually recommend the products, so I'm passing this user ID and then the top. So these are the recommended products for this user. Top 10 recommended products for this user. Once I get this top 10 recommended products for this user, then what I'm trying to do is basically this is just like println statement, like a debug statement. I'm reading another data set which has the movie name, link, and genre of that movie. Okay, the reason I'm getting this is instead of displaying the movie item number, like 123 movie is recommended for 789, I just wanted to say, okay, movie iRobo is recommended. So to get that name, I'm reading another data set where I'm splitting the data, okay, based on the pipe symbol and getting the first two columns out of it. And the first column is the ID, item ID, and then second. So once I get that information, movie ID and movie name, I'm just looking for this movie, look up for this 789 user. So movie for user. I think this is basically like ratings that keep. So this is like getting the movies for this particular user. And then I'm just sorting all the movies. So since I've got 10 recommended movies for this user, I'm sorting based on top 10, and then I'm just printing something like this, like a recommended movie is the movie, say iRobo for instance. So here, like I'm taking each rating and then titles dot product of and then rating. So for each of, so the next level dot print level. So I think what this guy is trying to do is this is iterating with all the top 10 movies and then just printing all the top 10 movies one by one in the list. Is it clear now? Ram? Any questions on specific lines of code here? Okay. So now that we understand the program, so let's go ahead and first build the program. So then what I will do is I will say SBT. So let me go to module 6. So this is in the package called module 6, but okay. So let me try doing this. SBT package. Let me see if it gets built or if it will have any issues. So once this project is built, I just have to place the files in appropriate folders and then we'll run the program, guys. Okay. There is some issue. So data bachelor import spark.ml not a member of core Spark. Okay. I think I had to change this build file. So there is another SBT file also. Build.sbt. Let me just copy this one. Okay, otherwise I can probably build using this also. Okay, let me just copy this. So I'm just changing the build file here. Okay, so please be patient. I think ours project is 1.6.0. Version 2.2. Okay, so now here also 1.6.0. Because of backward compatibility, even 1.5.2 also should work. But just I'm changing the build script to make it more synchronous. Okay, so now I think everything is there here. Okay, looks like pretty much everything is matching now. Okay, let's try to run this program. So now that I have the build file, so let me rebuild this once again. It will take time because I have changed the version of this jar. Hopefully they should go through. So once this program is done, we'll take a short break and then we'll come back and we'll reconvene on a SQL, Spark SQL module, folks. Okay, there seems to be an error here. Server access error, connection refused URL. Okay. Okay, the build is successful. Let me refresh the target right. So this color 2.2.0. CPMNT HGF desktop and then hello spark.2.2.2. Sure. Okay. So now that I have got this jar file as well, code, then spark -1.6. Now let me run the program here. Let me check if the files are there in the path or not. Hadoop fs-ls/user Embellizer. Let me check the path. Home Embellizer ML100K. Okay. Home Embellizer ML-100K. Okay, I have the data also in place. I just have to run the program now. So to run the program, all that I'm supposed to do is just run this. Spark submit, and then the class name is movie.scala. Movie, that's it. Movie, and then the jar file name is hello spark, right? So 2.2. That's it. Okay, so class name is capital M. Movie is it? Excellent. Movie lens ALS. Sorry, it's not movie lens ALS. Okay, so now that recommendations program has started, some problem has come reported. Input path does not exist. Oh, okay. I have to change it to just the absolute path. Okay. Let me rebuild the program again. So this time it will be fast because there is no version change, and since we have already built this project, it will be quick. Okay, so now the project got built successfully. Let me copy it again. Okay. Now this should read from HDFS, but still there is some problem, looks like. HDFS localhost 9000. Oh, why is it saying it does not exist? HDFS localhost 9000 home. Oh, okay. Sorry, guys. So it's a typo. Let me rebuild it again. So guys, are you all following with me? I'm just trying to test. No one is trying to recommend what was the error so far. I just wantedly typed to just check whether you guys are watching my screen or not. Okay. So now that I have rebuilt it. Okay. So now hopefully it should go through. Excellent. Finally we made it. Let's see what's the output we get. Okay guys, so the execution was successful and somewhere it might have printed the recommendation movies. See here, it has recommended top 10 movies. One is Godfather, I think, with the rating as 5, and then Train Spotting, Dead Man Walking, Star Wars. So these are the top recommended movies for this user 789. Okay, so you all understand now how you should create the models and run the models in the Spark framework. So Shakti says it was a tiny error, so I can't see it. Okay. Sure, Shakti, no problem. That's good. Okay, so now that we understood, right? So shall we move on further then? Okay, so finally, okay. So Venkat still has this question about TensorFlow. Thanks for reminding me, Venkat. So Google TensorFlow is a package basically. Okay, so they recently looks like they open sourced this package. So Google TensorFlow is also similar to Spark or even any other machine learning package. It's not so different. It's pretty similar, but the only difference is Google TensorFlow is basically built around something called as deep learning, which was crucial component within Google. So Google uses deep learning for various types of problems, like to build a Google goggles or maybe the voice recognition. You might have used this Google voice search, right? Now it's been used quite I mean, the accuracy is also quite good, Google Voice. If you see, you can actually say, and then it will start searching based on your voice. So internally, there is a model which is actually converting your voice to a text, with which it is able to do the text search, right? So deep learning is basically used for such kind of complex problems like voice search, voice recognition, okay, or image recognition, or then let's say identifying specific components within an image. So these kind of complex okay, so this is kind of bit advanced kind of algorithms, and I believe that Google TensorFlow has actually been built around this model, and they have made it open source. No difference. So maybe architecturally there could be differences, but we don't care about that. It can scale, that's what for sure, like similar to Spark or even similar to Mahout, it can scale as well. Obviously the performance, you could expect the better performance because Google developers has implemented it and they have been using this model since quite a long time. Okay. Only in terms of models, Spark has different kind of models. Spark does not have any deep learning models as such. One model they have recently implemented is artificial neural networks, but that is still in prior testing phase only. It's not really production use kind of algorithm. However, if you go back to Google TensorFlow, so that probably you can use it in production environments as well. So that even a layman without that kind of complex statistical analysis, he can actually go and use the Google APIs to be able to build such kind of complex products. Okay, Venkat. That's all about it. But if you are interested, you can go ahead and learn about deep learning models and all that stuff. Ideally, they will be using some kind of artificial neural network, some advanced artificial neural networks model to build a deep learning model capability. Okay. And that's a good package actually. It has a lot of scope for in the future, scope in future. Okay, too. Maybe it's quite early, right, for people to adopt. But once it gets quite strong because the type of applications are quite interesting with that, especially image processing and then the voice search. These could be typically the regular use cases from here onwards, folks. Okay, so that's all about it, and then let's go further. So what is DStream stands for? Annie is also sometimes very interesting, so she asks very interesting questions. So folks, please go ahead with your answers. What is DStream? Guys, did you see the question here? Okay, sure. So discretized stream, right? And then checkpointing is always required for streaming applications. Is it always required or not? Always not required, but it is user specific, user choice. Spark streaming can process data in HDFS, HBase, RDBMS, all of the above. All of the above, right? It can persist in any of them. MLlib has got the algorithms of Mahout, true or false? False. It does not have all the algorithms as in Mahout because it is relatively new package compared to that of Mahout. MLlib needs to be installed separately from Spark. False. It comes as part of the framework itself. So try to complete the assignments, and I hope you guys have enjoyed today's discussion, being very informative and exciting as well. So let's move on to the next module, which is module 7, folks. Okay, so how about a quick break here? So folks, I would like to at least complete 10 to 15, 10 pages at least, 10 slides, so that we could complete the whole session in the next week, first session. Okay, how about a quick break of 10 minutes? Everyone, I just got one response so far. Maybe we'll spend another like 20-30 minutes, not more than that. Okay, don't worry, I'll not take too much of time today. Anyhow, we just need another one more session to complete the whole project. Okay, sure. So let's go for a quick break. My clock is like 12:52 a.m. I'll come back at 1 a.m. So just go for 8-minute break, folks. Okay. Hi guys, are you all back from the break? So Venkat is saying that, okay, so guys, are you all back from the break? Quickly say yes or no. Everyone on board? Okay, so Venkat says one question here. So we thought of discussing about DAG, Kafka, and Cassandra example. Okay, so actually, Venkat, the project work we are going to do, right, which is the last module, module 8, that will cover this. Okay, don't worry about it. So that will cover Kafka, but I will try to cover Cassandra if possible, and at least I'll show you how to connect to Cassandra using Cassandra Spark connector. But the last program will cover Kafka. So that probably I will explain it theoretically. Okay, is that fine, Venkat? Sure. So guys, if you're all back from the break, so what we will do now, let's just a quick introduction about the Spark SQL module and try to get some hands-on experience on some of the basics of Spark SQL. It does not take too much of time. Let's spend around like 10-15 minutes and we'll skip the session from there. Okay, so this module 7 basically is dedicated for graphics, Spark SQL, and performance tuning aspects of Spark. So let's try to see what are the objectives for this session. The objectives are what is Spark SQL, then difference between Hive and Spark SQL architecture, SQL context, Hive context, what are they and how to use them, then data frames, JSON and Parquet file formats, visualization, Spark SQL in Hive, again integration between both of them. We'll also consider what is accumulator and broadcast variable. In fact, we discussed about it already and we have seen the example also. However, we understand what are they again. Finally, we'll end our discussion with graphics and graph specific algorithms today. Okay, so since we already recapped, I'm just going to skip this. So folks, Spark SQL is a specific package available in the Spark ecosystem, Spark framework, which basically enables any SQL developer easily able to process and analyze the data with simple SQL queries. So ANSI kind of SQL queries. So Spark SQL is used for structured and semi-structured data analysis. Then it becomes very useful where the requirements is to deal with mostly like structured data. So fundamentally, I mean, so far I've been interacting with at least 15 plus customers throughout my career. And when I say 15 plus customers, they are like my personal involvement, and I've been doing a lot for this. And there are like subcategories I've been consulting a lot as well with different customers. Most of them are actually trying to solve or deal with structured data. Even though sometimes they refer as semi-structured data, they are actually having some structure associated with it, because if you are referring to XML files, Excel files, so these they have some sort of structure associated with that. So Spark SQL module basically provides opens up the doors for the SQL developers to be able to easily analyze such data by writing SQL queries rather than implementing code using Spark MapReduce or Scala kind of languages, because there is a learning curve involved for you to understand the functional programming language and understand the MapReduce basics and then try to implement the code. So instead of that hustle and bustle, you just go ahead and write simple SQL queries and let the Spark SQL module take care of how to handle the data processing internally. And most of it is like SQL constructs are directly supported. So mostly it looks like ANSYS SQL. Then it can actually read the data from files. Multiple sources include like HDFS. So formats could be like JSON, Parquet, RDD files. RDD is Hive. So even you can read data from Hive as well. You can write the data to Hive. Either way is possible. So integration is quite good between Hive and Spark SQL. In fact, you can run Hive queries as is without doing any changes as well. So that's also possible. And then Metastore, so it can use the Metastore service. So what Spark does is basically whenever you write a Spark SQL query integrated with Hive, it basically connects to Hive Metastore to read the metadata of the Hive tables and all. However, while running the program, it does not use the MapReduce, just like the Hive uses the MapReduce, right? Traditional MapReduce. Instead of that, Spark uses its own way of computing or processing the data, with which it becomes more efficient using the RDD data structures. And Hive queries need not have to be changed, which solves a lot of migration hurdles. Let's say if you want to migrate the existing Hive project to Spark, you might sometimes migration itself comes with a lot of additional efforts, right? So you have to reinvent the whole thing again. But here, since Hive queries can run as is without any change, it becomes quite simple. You do not have to change anything to the existing queries. You just migrate them to the Spark SQL using the existing queries itself. And you get the performance. That's the whole story, right? You get the performance better than Hive, which could be sometimes equivalent to 100 times better than this Hive performance. So Spark SQL in detail, so basically Hive queries need not have to be changed. Hive queries are up to 100 times faster. It gives possibility of near real-time querying capabilities. Even though it's not real-time or it's not interactive query, but it supports near real-time querying on the data. Okay, but however, you can use Impala if you want to do the interactive querying on top of Hadoop. It also sometimes takes near real-time kind of efforts, but there are certain workloads which are good for Spark SQL, which are good for Impala, and which are good for Presto. So these are querying technologies available on Hadoop, right? And there are plenty others as well, but these are like most popular ones. And then future versions of Spark SQL will focus to basically enrich the data frames rather than focusing on the SQL part alone. So it basically is trying to enrich the data frames functionality, and so that you can easily be able to interact with R, and then it leads to the PL SQL capability support through Spark SQL for future. So here is a quick, just have a quick look at the Hive architecture. So Hive has something called as Metastore. This will be managed on some kind of RDBMS, where it keeps all the table structures, partitions, information, everything on the Hive Metastore. However, it goes to, let's say, client will basically interact with Hive using the Hive CLI or JDBC API, or even driver with some kind of client APIs like Java API or whatever. So using that, the client can interact with Hive. So whenever you write a query, basically that goes via all these things, right? It goes to the Spark SQL parser first. SQL parser will help you parsing the query. Then query optimizer will optimize your query. Then it will go through physical plan and the execution will be decided and the actual MapReduce will be created. The MapReduce program will get executed. The binary program will get executed via the MapReduce. And finally, it will retrieve the data from HDFS and will finally give back the result back to the customer client. So problems with Hive. So Hive is popular Hadoop ecosystem component, and it has been matured quite a lot. It has got a lot more functionality as of today, and it can't be just replaced just like that, but it can be used as complementary tool with Spark SQL. So Hive is more popular ecosystem component and is used for ad hoc data analysis on large data sets. So these are some kind of self-explanatory statements. Then Hive exposes a query language called HiveQL. Hive has its own language called as Hive Query Language. It does not look so different than ANSI SQL. It looks pretty much similar to that. If you are familiar with MySQL and querying with MySQL, it looks similar to that. However, certain things are a bit different, which you could learn quite quickly. So there is no lot of learning curve involved in writing high queries. And then high basically converts whatever the query you write in behind the scenes. It converts the high query into MapReduce job, and MapReduce jobs will get run on top of the Hadoop. The MapReduce enables very fast analysis of huge data sets and then lacks in performance. So one of the key bottlenecks is basically the performance, right? You have to wait sometimes minutes or sometimes hours as well, depending on the volume of the data and the type of the complexity involved in processing the data. It could be joins, it could be aggregations, whatnot. Okay, so depending on the complexity, the time could increase exponentially. Then MapReduce involvement means the response time will be in order of several seconds. So this is very optimal number you could expect, right? However, going with Spark SQL, it would be optimized quite drastically, and you can get 100 times better performance in some workloads, not all of them, of course. So Spark SQL, how does it look like? So unified data abstraction is you have the Spark SQL and the data frame abstraction, with which you can read the data stored in Parquet format, JSON format, Hive, or even Cassandra. So you can interact with Spark SQL using any of these underlying data stores. You can also communicate with Spark using the Python API or Scala API or Java or high query language or even SQL 92 kind of APIs. So there is a question. Satish says, does the high query optimization, which we do like bucketing, sampling, etc., still work when we run through Spark? Yes, it will still work with Spark as well. So however, right, the way it works is slightly different. So when you do bucketing, the data is stored in the buckets. The data is stored using some partitioner, and then data is stored using some number of partitions and defined by the partitions while you create the table, right? So when you actually create an RDD, so when you run a Spark SQL, it creates an RDD out of the existing data. Even when you write, you can actually enable that bucketing and then partitioning feature so that it writes up to the appropriate directories within the Hive. Okay, so it is still supported, Satish. So Spark SQL lets you query structured data as a RDD with integrated APIs in Scala. Shark project is completely closed now. So what this means is previously, even before Spark SQL was existing, there was a project called as Shark, or module called as Shark module, which is not available now. Okay, so this Shark module was designed totally by keeping in mind to support Hive. However, having said that, they realized the importance of other data stores, so they actually expanded the support for other data stores like Cassandra or file systems like local file systems and all. So that's why they have renamed the Shark to Spark SQL module, and by the support for additional data sources as well. So development ending, so and then the whole transition is happening for Spark SQL. Almost it has happened, I would say, now. So slightly, if you try to compare between Pig, Hive versus Spark pipeline, it looks something like this. In Pig, Pig basically uses Pig Latin scripting language, so that's why it's called as Pig framework. Pig parser will basically create the logical physical plans, an optimized logical plan for MapReduce, and then executor will run the physical plan. Hive also pretty much similar to analogous to Pig. You write the Hive queries, then Hive parser will create the logical plan, and then optimizer will generate the optimized logical plan. Then the actual physical plan, which is the actual MapReduce, will get generated and then will execute it on top of Hadoop. So both generates the MapReduce jobs by the end of the day. But if you look at Spark, so Spark supports Hive queries as well as Spark SQL. Spark has its own query language, so it uses Spark SQL queries and also the data frame. So all goes to a data frame, and then it uses something called as catalyst as underlying package, and then uses the Spark RDD code to process the data. So by the end of the day, it goes to the Spark RDD abstraction here. Even though you can interact with multiple channels here, you can write Hive, you can write Spark, or you can write data frame code. So we'll study all the three parts now. Okay, so I think this is like some of the programming aspects. So let me go back to my VM to run some programs here. So we'll take another like 5 to 10 minutes, folks, and then we can stop the session there. We can take a logical break, just another 5-10 minutes. So in order to launch Spark, what I will do is I'll just go to Spark Shell. I'll launch Spark Shell first. So once the Spark Shell comes up, so here are the steps. So these two steps are not required anymore. So just at least forget about high context. We'll discuss about this later. Spark SQL context will be available by default now. From 1.5 onwards, SQL context is other instance which is available by default in Spark Shell. You can use both the SC, which is Spark context, SQL context, which is SQL context. Okay, so you can see here SQL context available as SQL context here. So you can write direct SQL queries using the SQL context instance. So now that we already have the SQL context instance, what I'm going to do is I'll read some file from HDFS, okay, which is called as people.json. So let me first type that how it looks like. Hadoop fs-text home embaliza and then module 7 people.json. Also, so this file has some data in JSON format like this. Okay, it has got name and age. So let me try to read the data using the SQL context. So what I'll do is I'll just use the SQL context object and I'll invoke a method called read and then JSON and then followed by the actual path from where the file has to be read. This will create a data frame for me. This method, JSON method, will return a data frame. So you can see here, it just has returned a data frame out of the query, and the data frame schema looks something like this: age, name. So age is a big integer and the name is a string. So if I say df.show, it basically prints the contents of the file like this. Okay, so now that I'm able to perform some basic operations using data frame, now I'll say val people equal to sc.text file of two data from. So this is another form. So you can directly do that, otherwise you can say sc.text file. So using text file also you can use this toDF method to create the data frame. So the first approach is use the SQL context and read the files. It will create a data frame. Second approach is use the Spark context using the text file method, using the method toDF. Basically you are creating an RDD first, and then there is a method called as toDF method in RDD. Using that method you create the data frame. Okay, so this is another approach. So I have to check whether this people.txt is available or not. People.json is available, so let me change this to JSON. So it just read everything as if it's a string. Okay, so if I say people dot show, it just prints as if it's a string. Input path does not exist. People.txt. Okay, I have to change this to JSON. Okay, so it just considers everything as if it's a string rather than it's a JSON file. Okay, so this way you can perform some simple basic operations either by SQL context or by Spark context instance, folks. So now I'll read some JSON file from using Spark SQL context. So I got employee.json here. So let me read employee.json. Call that as employee. So by default, it will be read as a data frame. So once I read the employee.json, so let me show you the contents. Maybe I haven't shown you the content here. Okay, it has got the name and then address as a structure, okay, which has city and state. So this is the structure of the employee.json. So Satish has a question, says, is data frame similar to a view? Not really. It is not like a view, but rather data frame is like a table. Okay, it has got some specific set of functionality, Satish, in a data frame. We can also perform table operations as well. I will show you that as too. Okay, there are two ways to process the tables in Spark SQL. You just directly process using data frame, which has some specific additional functionality. If you want to write some kind of SQL queries like select star from employee or select star from or where, for example, so that also is possible, but you have to do it slightly different way. I'll show both the approaches. Okay, but data frame is not a view, for your information, but it is just like a table with some specific functionality related to statistics and all that stuff. Okay, so now that we have read the employee, so the first thing I'll do is just I'll print the schema. Okay, using print schema method. So it has this schema, address and then the name. Then what I'll do is I'll register this table, I'll register the employee data frame as a table. So to do that, employee.register temp table of employee. By invoking this method, register temp table, employee will be considered as a table now. It's not a data frame. Now you can run select star kind of queries on employee table. Say for example, I can do this now. Val employee data is equal to SQL context.SQL. So you have to use this .SQL and then write the SQL query like this: select name, address, city, address.state from employee. This is like running a SQL query, right? So it just returns the employee data, and then you can print that employee data using the for each, collect and for each method. Okay, employee data collect of for each of println. So it prints the values as if it's a tuple. So Ram says, how about the partition in this case? So Ram, so far we are actually not dealing with Hive. Okay, we are only dealing with Spark SQL. So in Spark there is nothing like storage, right? So you don't need to worry about how the partitions happen in Spark. But while working with Hive, what happens is while writing the data to Hive, you should be careful. You should know what kind of partitions that Hive has. Accordingly, you have to decide how many number of partitions to be used. So that I'll show you in a moment when we discuss about Hive context. Okay. So Shakti says, why are we registering the temp table here? Okay, sure. Let me explain that concept once again. So in Spark SQL, there are two components. One is data frame and one is table. There are two concepts. One is data frame and one is table. Okay, data frame is an object. It's not a table. Okay, it's just a type. Data frame is just like a type. It will have some kind of functions. Okay, let me show you the functions in a data frame. Okay, so I'm going to APIs. I'll say data frame here. So if I go to data frame, you can see there are some functions in the data frame like collect as list, count, describe, first, head, show. Okay, these are various functions available in a data frame like aggregation functions, apply, column, cube. These are all what? These are all functions. Okay, let me take one example to explain you in a better way. Let me take the count here. For example, there is a count function, right? Somewhere here there is a count function. Where is it? So here is the count function, right? Here, if you look at the data frame, if I have a data frame, for instance, like this, XDF, like it's a data frame, in order to compute the count, calculate the count, I'll just say count of. It will return me the count, let's say 100 records. Okay, this is how you compute the count. But you can actually convert a data frame to a table by using xdf dot register as temp table. This is a method. You have to pass the table name here. Table name as in some table name. Okay, like let's call it as x table. Okay, this is some table, right? So now you say x underscore table dot SQL of Spark SQL context dot SQL of, I think it is, sorry, SQL context dot SQL of. In order to calculate the count, you are supposed to do this: select star from x, select count of star from x table. This way you are supposed to calculate the count. So what is the key difference registering it as a table versus using a data frame? Using a data frame, it's an object. It has some functions, some built-in functions, but you can't achieve everything just like you do in a query. Using SQL, you can do a lot of things, right? But all those things may or may not be possible with a data frame. But it gives you certain level of abstraction and ease of use for programmers, and data frame kind of concept is mainly used by the data scientists or even programmers too. However, coming back here, for a SQL developer, using this kind of code will be bit complex for him. He would rather prefer to write SQL queries so easily rather than writing this kind of code. So that's where you actually have to convert or register the data frame as a temporary table. Then you start writing the SQL queries. Then you pass the Hive queries as well here. So do you now understood the difference between both of them? Shakti? Then Biswajit says each table will be session specific or permanent for other user as well. Very good question, Biswajit. It is session specific only. It's not permanent. It is session specific, Biswajit. So every time you have to create the tables. Okay. So you might ask me one question. So it's kind of redundant, right? So yes, but if you use Hive with Spark, you don't need to create, right? You just have to read the data from Hive. That's it. So that time you don't need to create the tables again and again there. Okay, so Shakti says only certain predefined methods can use. Correct. So if you are using data frame, only specific predetermined functions could be possible here. But using a table, you can write all types of queries using SQL context. So I hope now it is clear for everyone. So now that it is clear, even I can run some queries like where conditions and all, right, using this. I can write a simple where condition like SQL context, select name, address, city from employee where state is equal to California, for instance. And then in order to print every time, you should do this state.collect of for each.println. So be aware, collect may not work every time, okay? Because collect, if you are dealing with a very big RDD, it will not work. So you are supposed to use take of 10 and then dot, something like this you should do, okay? Or maybe take of 2 in our case. Just returns 2 records. Take will work, but not collect if you're working with a really distributed RDD. Okay. So let us complete this Parquet thing and then probably we can stop there after completing the Parquet. Shall we complete the Parquet or shall we take the break here? Guys, shall we take a break here or we can complete the Parquet thing and then we'll take a break? Excellent. So pretty much everyone say let's complete the Parquet file format and then we can take a break. Good. So let us discuss about Parquet thing and also Hive also we can complete looks like. So let's see both of them. Employee save as Parquet file, for instance, right? So you can actually save the file as a Parquet file using the save as Parquet file method. Oh, sorry. Let's say module 77. Okay, employee dot save as Parquet file. That's it. It will save the file as Parquet file. So the file has been saved as Parquet file. Let me show you that file. Now if I say Hadoop fs-ls/home embelliser and then module 77 slash. So it has employee.parquet. So emp.parquet. emp.parquet will have the Parquet files here. So part1 dot, it will have this format here dot Parquet. So do you know this Parquet file format, right? So this basically is used for maintaining the structured data on top of the file systems like HDFS. And it is more efficient and it also applies the compression algorithms as well to compress the data. So if you are using Cloudera distribution, mostly the default format at the moment you can use this Parquet. If you go with let's say other distributions, for instance Hortonworks distribution, the preferred format to be used is ORC format. Okay, optimized record columnar format. So then now that I have stored the file, in order to read the Parquet file, it's very simple. Again, you say SQL Parquet file. So SQL context.parquet file, sorry, not here. Val Parquet file is equal to SQL context.parquet file, and then just pass the path here. Then let me change the path also. So it has read it as a data frame now. So just Parquet file.print schema, it just prints the schema of the Parquet file. So this is how you interact with Parquet file format, folks, by using the methods like save as Parquet file or register temp table. It's again the same story. You just register the Parquet file as a temp table because it's a data frame, right? You can just perform the data frame like operations and then query the data just like you queried just before, because it's a data frame by the end of the day. I'm just printing the values here. Okay, and then you can store the output Parquet state into some path. Parquet state.save as Parquet file again into some path here. You can just move this and they can store like this. So I'm trying to store the resultant data as a Parquet file now. So the resultant data got stored as a Parquet file. If I just show this, it will look something like this. So Parquet output. If I even try to print this file, right? So it just prints as if it's a binary file. See here, the data is somewhat printed as a binary format because these formats internally use a different binary format to store the data in order to be able to compress and efficiently read the data out of the file system. Okay, so far any questions, guys? Anand, is it clear about Parquet file and the ORC file format? So basically they are like they're the most popular formats available today in Hadoop ecosystem. They are used extensively, especially these formats are derived mainly for two reasons. One is for performance reasons and the other one is for compressing the data efficiently. Because without using these formats, right, if you try to compress the data, it may not be that efficient to read it. Using this format plus the compression will give very good results, because think about the scenario where you are dealing with some terabytes of data every day. You can't afford to keep the data as is into the file system. You might want to compress the data, okay, so that you can achieve very good compression rate, like at least 3 times or something like that, or maybe 30% of the compression ratio. To get that, you use these kind of formats, and also at the same time you're having good performance, especially while reading the structured data, either with Parquet file format or with ORC file format. Having said that, the rule of thumb is, if you are on Cloud Era, just go with Parquet. If you are on Hortonworks, just use ORC file format, okay, which gives better performance in their own regions. Then Satya says, considering the Spark SQL tables are not permanent, could you please explain with a use case? See, Satya, as I told, yes, Spark tables are not permanent because you have to, every time you have to create like this, and they are like very session specific too. Okay, these are used just for manipulating here, right? So you can write it even in a script and you can just run every time, and they are good for handling the data like this. But The reason why it is like that is because Spark does not have its own storage. When you interact with, say, Hive, then obviously you do not have to recreate the table. You are just reading the table data directly from Hive. In a moment, I'm going to show you that example to how to read the data from Hive and how to write the data to Hive table. So there you might not have to create the table every time because the schema is already fixed and you're just reading from the Hive meta store there. Satya. As I said, in use case point of view, usually if you're trying to process the data in Spark for non-structured data sets, then you create scripts and you just run the scripts. You don't use Spark Shell in a production environment. You mostly write the scripts to process the data. And then Satish says, so the SQL Spark queries which we write can be read binary data. Yes, of course. It depends upon the support for the format. Even we support like sequence file format, so you can read the data in sequence file format too. If you are having any specific binary format which is not supported by either sequence file format or Parquet or even ORC, then you might have to implement even a customized format in Spark SQL to be able to get the support. Satish, it just not means that if you have some other type of binary format, can it be read? No. You have to implement that kind of input format or output format to be able to read and write. Okay, so that's pretty much it. And coming back to Hive is like very simple and straightforward. All that you are supposed to do is just do this. Okay, you use the SQL context.SQL, create table if not existing customer like this, and then Spark SQL this one. So however, in order to be able to integrate, you have to have the Hive site.xml copied into your Spark. So in your Spark, you have to copy the Hive site.xml. Okay, let's do one thing. I think we have covered pretty much now. So since Hive is kind of a bit interesting concept, let's not do it quickly here. Let's take sufficient time in the next week and then we do it in the next week, folks. How about that? Shall we take a logical break here and then we come back and discuss about Hive integration with Spark, and then we also cover graphics module in the next week. Also, we cover the project as well. I think we'll have sufficient time. Project work will take hardly like 1.5 hours. And in the remaining 1 hour or 1.5 hours, we should be able to complete the remaining topics here. Ram says, in real time, do we use only Hive query language and Spark SQL together? We can use both, Ram. Depends on what types of where the data feeds actually reside. But it is combination of both, Spark SQL and Hive. Okay. So guys, any questions so far? I hope you guys have enjoyed the session, even though it's a bit lengthier session. Since we have actually discussed about very interesting topics and exciting too, so I hope you guys really followed and you enjoyed the session, guys. If you have any questions, if you'd like to speak to me regarding anything, I can unmute you guys so that you can speak to me directly now. I think we are pretty much in line. Okay, so we just need one more session. So please don't forget to join another one more session. So next week on the Saturday, we should be able to complete everything. Okay, with just one additional session. Excellent. I think there were no questions. The same time, I mean, today's time, right? Whatever today's time will be the same for Saturday as well. Ram. Okay. So guys, I hope you guys have enjoyed the session for today, and especially being informative. I think please try today's and yesterday's discussions. before you come back for the next session. Okay, so please do not miss the last session. Probably we'll also have some kind of send off and then. Okay, bye for everyone.